Dear students, next we will briefly go over Kubernetes, aka K8s, which is a container manager / container orchestrator / cluster manager. Okay, why do we need such a thing as cluster manager? Well, in DevOps world, in the operations part, online services are critical, and there is the assumption that software is always available. So users basically do not care if poor software service is due to operations failures or development failure. And Cluster Manager can help us avoid failures in the operations. Things that may occur during the operation is that the runtime load can vary a lot. So if you think of a ticket sales system, you would normally have quite low load, and especially maybe during runtime you might not have any load, but there might be high peak low demand. For example, when popular tickets go on sale, for example for the football World Cup or maybe of some famous band. So when those tickets come available, then the load can be 100-fold or even 1,000-fold. And it is not unheard of that these systems go down as there is not enough server capacity to serve all the clients at the same time. And this is something where a cluster manager can help. Obviously, this help is only to the degree that you specify, that you have enough hardware. So if you run out of hardware, then you have no help here. But it can certainly help in the load balancing and load scaling up, and also load scaling down. Load scaling down is also important because we don't want to pay extra for the services that we are using. So we have a load balancer part of the cluster manager. And since we are talking about containers, we can also say container manager or container orchestrator. They would all mean the same thing in this context. So Kubernetes is one cluster management software, but there are many others, as we can see from this list of cluster management software that is in Wikipedia. We have Docker Swarm, we have OpenShift, we have Rancher from Rancher Labs, CoroSync from Cluster Engine, and so on. So there are many of these types of software available. However, Kubernetes seems to be the most popular. If we look into Google Trends, which lists the number of searches done with different search terms in the history, we can see that I have prefetched Kubernetes on blue, OpenShift on red, Docker Swarm on yellow, Elastic Container Server, which is from AWS, Amazon, and then a Microsoft Cluster Server as 5 different options here. And if we look at the number of, this is the relative number of searches, so this is not an absolute number here. But if we look at the week 25th September versus 1st October, we can see that Kubernetes had a search number of 76, while OpenShift had a search number of 13. And during that time, all the others had zeros. So from the past 18 months, we can see that Kubernetes is the most popular, then is OpenShift, and Docker Swarm also has some popularity. We can also go a bit further. So if we take past 5 years, we can see that Kubernetes is consistently the most popular one. We can see, I can only find the 1 month where Docker Swarm would have been more popular, which is here, or during Christmas. It seems that yes, during last Christmas it seemed that OpenShift was slightly more popular than Kubernetes. But otherwise Kubernetes has been the leading one in here. And this is in Finland only, but the situation doesn't change if we take the entire world. So what we can see here is that, well, the differences are perhaps even bigger. So it seemed that in Finland, at least OpenShift and Docker Swarm were somewhat more popular, but throughout the world, it looks like Kubernetes is really the most popular one. And just one point regarding the Docker that we have previously discussed. The Docker Swarm that is talked about here is not the same as the general Docker. So Docker Swarm is the container manager, which is equal to the Kubernetes, while Docker is basically just the container runtime. So there's a difference there. So when you see a Docker Swarm, it is a different thing than Docker by itself. Okay, so if we briefly look into the Kubernetes architecture, it currently supports multiple container runtimes. So you can run the Docker engine, container D, then you can run CRI-O, and Mirantis container runtime. And these containers always reside within a pod, and the pod resides within a node. And well, the containers, they are as previously explained. So a brief recap. So this was already covered in the previous lecture, but in case you have forgotten. So we have different levels of isolation and different ways of isolating processes and running software. So let's assume that we have my database application, and then we have a web shop on top of it. So you have two applications, my database and web shop. And if you use just the process level isolation, where you just isolate the address space, but there is no isolation for files or networks, this is very lightweight, and basically it corresponds to this bare metal picture here. So you have a single machine, you run it in your basement, you run two apps on it. You have the database where you have all the data items, and then you have the front end shop that you run on top of it. And then you run it on your Windows or Linux machine, and you're very happy with it. It's very lightweight. And it used to be that all web apps were run like this. But then at some point, someone realized that, maybe it doesn't make sense to run everything on the same. And the virtual machine was introduced. So the benefit of virtual machine is that the MyDB and your shop now are isolated for files and networks. And you can also run them on different operating systems. So you can run something on top of Windows while the other one runs on top of Linux, for example. And then you have the hypervisor that controls these operating systems. The problem with the virtualization was that it was very heavyweight because you had to take the entire operating system with you. So it took a lot of space to have all the operating system libraries there. So then what emerged was container. So container is kind of like in between of the process isolation and virtual machine isolation. So it tries to take the best from the both worlds. So you still have isolation in the address space and also for files and networks. But at the operating system level, you run the same operating system, so it becomes much more lightweight. And container is sort of, you try to get the benefits from the virtualization, from the virtual machines, but you try to have them on lightweight. So that's why you do containers. Okay, and here we can see containers inside of these blue rectangles, and they are at the lowest level here. They are the smallest entity, and they are as explained in the previous slide and also in the previous lecture. So in Kubernetes architecture, all containers run inside of pods. And now what are these pods? Well, they are a set of non-isolated containers. So they kind of break what was said about containers here, that they have isolations for files and networks, because inside a pod, they do not have this isolation. So according to the definition, it's a set of containers with shared namespace, this is network, and shared file system volumes. Inside a pod, there can be one or more containers which are relatively tightly coupled. And they would be tightly coupled because they share the namespace and file system. And if we sort of go to the non-cloud context, applications on the same physical or virtual machine are analogous to the cloud applications executed on the same logical host. So if we go to the physical world, these pods correspond to this case here. So this bare metal case where you only have process isolation. So you have MyDB and MyShop, like the things that they used to be. And then you basically share everything except the memory, the address space. But everything else is the same. So it corresponds to this setup, this bare metal setup here. Okay, so continuing with this container pod node. So all of these pods are then run inside of a node, and this node sort of corresponds to the virtual or physical machine that hosts the pod. And everything that happens on a node is guaranteed to happen in the same virtual or physical machine. So inside of Node, you have some management software. You have the container runtime, which can be the Docker container D or CRO or other container runtime. In the image, I've just written Docker in parentheses, but it can be also other runtime. Then there's other management software inside the node. There is the kube proxy, which handles node networking management. And then you have kubelet, which manages the pods and the containers, checks that they are healthy in collaboration with the container runtime. So a bunch of management software is then added on top to ensure the healthiness and the running of the containers. And since Kubernetes is a cluster manager, you would have multiple nodes running, which all are the same. So they have the same architecture, and then you have a master that is controlling these nodes. So inside the master, there is a bunch of management stuff that you use for controlling this cluster. In Kubernetes, you have something known as controllers, which basically regulate the system. So you could think of like a thermostat of the system for a room. So you set the desired temperature, and then the thermostat starts to work on getting the desired temperature to the level it needs to be. So it tries to move it to the closer to the desired state. So for example, a deployment controller, you describe the desired state of the deployment, and then based on the desired state, the deployment controller starts to change the actual state to the desired state at the controlled rate, while also being considerate about the healthiness of the overall cluster. Then there is also a job controller, which creates one or more pods and will try to retrieve the execution of the pods until the specified number of them successfully terminates. So it sort of ensures that that things get done in the cluster. And as the pods successfully complete their tasks, then the job controller tracks the successful completions, and when a specified number of completions is reached, the task is complete. And deleting a job will clean up the pods it created. So this manages, if you try to do something, it creates the necessary pods, and inside the pods you have the containers that do the things. And then after the job is done, you have enough successful completions, then the pods get deleted and you get like scaling down of these resources. And the job controller also supports suspending. So if you want to suspend something and then resume it later, suspending a job will delete its active pods until the job is resumed again. So it also scales down the resources, and scales them up as needed. Then you have a separate component as a scheduler. So this watches for newly created pods. And these pods were created by the job controller. It watches for the newly created pods with no assigned node and selects nodes to run them on. So this is basically a scheduler that makes scheduling decisions based on the resources available. So it can see that, okay, there is a virtual machine or there is a node that has a low computing load at the moment, so it has a lot of resources available in the node. So it pushes it assigns those pods to the particular node, so it takes those resources into use. And as you can notice, there is pretty strict and pretty fine-grained responsibilities here on the server side. So the job controller is only interested in creating and destroying the pods and watching the successful terminations when it knows that the job is done. But the scheduler it doesn't know anything about what the pods are doing and doesn't care whether they succeed or fail. It just watches newly created pods and assigns them to wherever computing power is available. So even those two tasks, one could think that they would be under the same software, but here you have the separation between the scheduler and the job controller. And there is more of this sort of fine-grained responsibilities divided in the master level. Then in the master you also have API server, which is basically a front end to the Kubernetes master, also known as the Kubernetes control plane. So it allows you to actually use the controllers, use the schedule, use the other features that are there. So this shows some of the components that are available in Kubernetes. Only a few of the components in the master were covered, slightly more on the node level, but there are more components there, and then there are more details. But hopefully this is something that can help you in working on the exercises.